About the optical design, and I start immediately on this because it's very important. You have two ways to develop your gonio. You need to illuminate the surface, and you need to measure the surface. So one strategy is to illuminate with a very large field, and you look inside the surface with a focus detection, like a spectroradiometer will do, for instance. You look inside the beam. And the other strategy is the opposite. You illuminate with a very focused beam, and then you have a detection with a very large field that is overfilling the illuminated part. And both of them are done. Both of them are possible, and they have advantage, and they have inconvenience. So if we go first on the illumination with a large field, example is here, for instance, you have the sample, and you see the illumination is overfilling the sample, and then the detection will be focused inside the sample, and this is what will define the field of the measurement and the illumination, the measurement surface that I called A in my slide at the beginning. To do this, you need to first to be sure that your light source is very homogeneous in terms of irradiance, and it's not always easy. For instance, here you see it's the output of an integrative sphere that is used to be sure that the light is homogeneous and on the sample. So usually you have a lot of use of power, so you need a very high power light source. So this is a problem. What is good is your detection is looking in a very small field and not outside. So you're less sensitive to the stray light of the room, in fact, because you are looking really, you're measuring really on the surface that is just on that part here. And that way you can use a picoamp meter for detection system, because detection will be silicon photodiode, you will get to photocurrent. One problem is that you get, with this, you get vigneting problem on the detection, because when the detection is rotating, your field here is getting larger and larger, and it can become larger than the illumination. So that's a problem, you have to be careful. Usually those people, they have different size of fields that they adapt according to the direction, the zenithal angle of detection. And you get low flux because usually you don't have so much power. That one is excellent. That's why I took this device. But you have a lot of power here, but usually it's not like this. But in fact, you have low flux always. So, at the opposite, you can make the choice to have a focus illumination beam. So you illuminate only one part on the sample, and then the detection is looking overfilling illumination. When you do this, you have less vigneting problems because the beam is small. Well, you have to have a detection that is, but it's less critical in this side. You maximize the flux because, in fact, you collect all the illuminated part. Where for the, that's what I forgot to say here. For this part, you have only one part of the sample that is taken into a part, one part of the illuminated surface. In this way, because you look on a large field, you collect all the surface, you maximize the flux. One problem is that you need to control the convergence of the beam. And this is because when you will try to make the direct measurement, if your beam is diverging much, it will in the detection. What is not good at all is that you are looking in a large field, so you collect all the light. So all the part that is not illuminated must be black, why it's stray light. And this is a very, very big problem. The only way to deal with this is to use a lock-in amplifier. And the lock-in amplifier, it's not it's not very easy to use, but then it works. And finally, I thought I removed this. No, okay. I should have removed it. So this is a too big design. I hope you understood, or at least you can come back on those slides if you want to make a choice at the moment. Now, if we go on the light source, this is the main problem usually because in gonios, you always have very low fluxes measured. It's very simple to understand. Usually you eliminate the sample from a given direction, and imagine if it's just a spectralon, which is a nice sample because it's white, so it reflects light, and it reflects light in the full hemisphere. So it's what we call a friendly sample. Even a friendly sample like this, imagine that you are trying to measure the BRDF within an angle of plus or minus 1 degree. So it gives you a solid angle of about 1 millisteradian. So it just, and the full, and the hemisphere, it's 2 p-steradian. So in fact, you have a ratio of the flux collected according to the eliminated flux of 1 millisteradian by 2 p-steradian. So about 1 × 10⁻⁴. So 4 decades of difference. And and this is a friendly sample. So you never have flux. So you need a lot of flux. The power of the light source is crucial, mainly for the detection focused, as I told you, because you will illuminate larger than your sample. The excitance or the emittance of your light source is crucial for focused illuminated device, because what matters is not really the power. What matters is the ability you will have to put the power on the sample. And this is the limited parameter is the excitance in this way. Your spectrum must be balanced because if you just use an halogen, you will not have any blue, and in the blue you will not perform measurement. If you color, you're dead. And the stability must be very good. This is also important because usually you need to make the ratio of the flux reflected in the direction by the illuminated flux. But in fact, in practice, what you will do is that you will measure the illuminated flux. Then you do all the geometries of the reflected flux, and then you come back to control that your beam has been stable. But if during the time you had a variation of the light source, when you are measuring your reflected flux, you make a measurement error. So there is possibilities to monitor the light source, but you need really to have something very stable. So the candidates, I put them here. You have the xenon arc. Xenon arc has a good excitance, has a lot of blue. The problem of the xenon arc is that the stability is very bad at short term because it's an arc, so it can move a little bit. Sometimes, according to your optical design, it can be a disaster because it will change the direction. Imagine if you put your arc as the focal of a lens, and then you have a beam that is collimated after your lens. If the arc moves a little in the direction of the beam after the lens change, and your gonio is there to keep the direction of illumination constant, and only the arc, if the focal is short, it can give rotation of the illumination. So it's a very bad thing. So be careful with the xenon arcs. It's not always appropriate. Quartz tungsten halogen lamps are really good. They have a lot of red. They don't have blue. The excitance is not that bad, in fact. So I should have removed. I'm sorry, I made modifications this morning and I don't see them. So unfortunately, I'm afraid I didn't save my file. Anyway, the excitance is not that bad, but it's less than the xenon. the stability is really good. So in fact, the QTH lamp is excellent for that application. The only problem is that there is no blue. You have what we call laser-driven light source. It's exactly like a xenon, but instead of having an arc, you have a pump laser that is focused on the xenon, and it gives a plasma that produce light at a given place. And this is really good because you have the advantage of the xenon without the instability of the arc. The problem is that it costs about 20,000 euros for one lamp. So you have to be ready. And it takes a lot of time to warm before being stable. And the last possibility is LEDs. LEDs, the problem is that they have a very low power. So for field illumination, don't think about it, but the excitance is really good. So sometimes you can use it. If you are in the focused illumination, you can use it. It's cheap. And it starts to be stable, but less than the QTH.
Can you come back on the problem of the stability of the source and explain again? It's important. Get it.
The time, the stability in flux according to the time, it's because usually what you will do is that you measure the incident flux by putting the detection in front. And you say, this is my phi I, my incident flux. And then you go on all the phi R of the other direction. It takes 1 hour because it's rotation. And then during this hour, you assume that your incoming beam is still the same.
Okay, I follow you. So, but is it not possible to splitter just after the source and to make a synchronous, so to keep track?
Yeah, that's what we do. We do what we call a monitor of the beam, but when you do this, you lose flux because of the beam splitter, and you already don't have a lot of flux. So sometimes you don't have the choice, in fact. Otherwise, you don't measure anything. So yes, you can monitor, and even when you monitor, it's always better to have a stable light source. So that was my point. But you're right. If we monitor, it's okay. It's better. For the wavelength, so I told you that you need to control the wavelength. You have two ways. You can use a monochromator. So the monochromator will take one given part of the spectrum. What is cool with the monochromator is that you control everything. You control bandwidth, you control the wavelength if you are well calibrated. You have to be careful to be well homogeneous at the exit of the beam, because what we do usually to make the things good is that we want to you have usually the filament of the lamp that is imaged at the entrance slit of the monochromator. We do this because we want to have the filament at the infinite on the grating, because then it gives a better diffraction. If you image your filament on the grating, it's not good. So you don't have the choice. If you want the filament at the infinite here, it has to be imaged here. So you get the image of the filament on the exit slit, and usually that's what you project on the sample. If you project the filament on the sample, it's completely non-homogeneous. So then you need another optical system here to be sure that you project something different. I just say that be careful to not forget to do this properly. That's all. Another way is to use a spectroradiometer. Then you do the spectral measurement on the detection. You illuminate with a broadband light source, and you measurement on the detection using a CCD sensor inside the spectroradiometer. So the grating is here, and you get the wavelength here. This is cool and fast because you can do a full spectrum very quickly. Be careful of the non-linearity of your spectroradiometer, because remind that on a friendly sample, between the measurement on the incoming beam and the reflected beam, it's 4 decades. For decades on a spectroradiometer, sometimes it gives errors of about 5–10% if you don't calibrate it here. Because you have very short time of exposure time for the incoming beam and very long for the, and then it's not made for this, so be careful. Only on detection, then you can only eliminate your sample on, you can only make the detection. So, sorry, you can only control the wavelength on the detection. Well, it's not a problem, but it can be. You have a fixed bandwidth that is given by the size of the pixel, so you don't control it. And you have also a fixed spectral resolution usually. With the monochromator, you control everything. One other thing interesting is the relation between your design and the angular resolution. That people usually don't think about it when they do. Imagine that you decide to have a beam of 1 centimeter of diameter, classical, to explore the appearance of your surface. So you design here a collimated beam to control the direction of illumination with an optical system. You have your beam, and here you have 1 centimeter. When you are looking at the worst configuration is always when you look at the sample, you measure in the normal of the sample, and you illuminate at a given zenithal angle. Because the projection here of the beam will increase when the zenithal angle will increase. The beam here will expand because of the projection. And then with the detection, when you look at the sample, what you look is at the light that is coming from all these directions. So in fact, your angular resolution is this angle. If you are not too, so your zenithal angle is not too high, it's okay. But imagine if you are, for instance, here at 80 degrees, your beam of 10 millimeters, it's now 57.6 millimeter. It's 10 divided by cosine 80. And then if you are at a 1 meter distance, in fact, what you are looking is at the properties of the material within all this cone here. So it's 6.6 degrees. This is the situation, the worst, always the worst situation is when you look at the sample from the normal. Just keep this in mind. Then maybe you can decrease, you don't really need 10 millimeters. As I told you, in the measurement equation, you have the solid angle here. So you need to well control your solid angle. The solid angle, of course, it's the ratio of the area here divided by the distance. You need to control the distance. The distance is at a square power. So if you make an error, you pay it 2 times. And for instance, when you are rotating around the sample with a ring of 2 meters or 1 meter of diameter, are you really sure that this ring is circular? How do you control the circularity? If you change by 1 or 2 millimeters, then it enters at a square inside the solid angle, and it provides error. You also have to be careful. Usually we collect in big surfaces here because we don't have a lot of flux. So you have to have a good aperture here, and you have to know very well the surface of the aperture. And you have also to have a good sample holder, because what is not, we always put this, assume that the sample is at the middle of the gonio, but in fact it's not that simple to find the middle of the gonio. You very quickly have few millimeters of errors, and then it will enter in the uncertainty of the calculation because of the solid angle. Again, since the beginning, we assume that everything is very homogeneous, but it's not true. At grazing angles, your beam here is very large on the sample, but your detection is still here. What is really the geometrical extent here? You have to be careful. You can't really assume that this surface is small according to the distance here. And sometimes you really have to do the integration of the full geometrical extent, which is the case here, for instance. I can't say that this distance is the same than this distance. So the solid angle in this part of the illuminated area is different than in this part. You need to do it. And I don't know if you're happy with this, but if you have a square beam here, circular beam here, and the square is projected from a given zenithal angle, it gives the losange. And you have to do the integration. About it, you will see, you will go to your fundamentals of optics. And it's not on the web. I mean, you can't just say, I need to have this geometrical extent by the square with a circle. Yes. Which one? Yeah. I hope for you. No, that's a game. If your beam is not homogeneous here, then, and if your surface is not has not the same optical properties along the illuminated surface, then yes, yes. You have to, well, on my side, what I do is that I split the illuminated surface in small surfaces, and then I compute the value of the solid angle for each of them, and then I sum. That's the only way to get the true radiance, in fact, within the Yes, because you can't find, except with two circular area, you can't find the full development of the geometrical extent. Well, I didn't find it. But you can solve it, but it's not easy necessarily when you are in space with two, where you are not in the plane of illumination. It starts to be a bit complex to find the directions and the length of the direction. But frankly, if one day you are stuck with this, send me an email because I can help you. I've been through that. What is that? This is, oh yes. This is something else also. It's about the angular resolution of your system. Usually, you assume that your system, you want to make a measurement within a given, with a given angular resolution, but you need to, your angular resolution depends on the size of the detection aperture. And this is, in fact, this angle, driven by the solid angle. That's what you think, but it's not completely true because on this side, you have a light source that is collimated usually, but this light source is not perfectly collimated. The light source is, the collimation depends on the size of the object you have here. So if your object has a given size, and it always has one, then you have a divergence of your incoming beam that is given by this delta theta high, that is the size here according to the focal, yeah, divided by the focal. And sometimes you really think that if you close your detection, you will increase your angular resolution. It's not true. Important is have theta high smaller than the delta O, theta O here. That's what I put on the slide, I think. Yes. And the resolution, this is the smallest of the two angles. This is, yes, this is Now this is the max. So this is the max of those two angles. So you can be limited in the detection, but also in the elimination. And then if you want really to decrease the resolution, you need also to decrease this angle. And if you decrease this angle, that means that you reduce the size of the incoming beam, then you don't have flux. So it's always a compromise at the end between all this. This is about alignment. It's not easy to align the things in a gonio, to be frank. And I have few people from SUPOP who are in my lab quite surprised that it's difficult to spend a lot of time to align the things, because it's 4 degrees of freedom, 7 if you take the translation. If you can get something at 0.1 degree, you're really good. And 0.1 degree, if we simulate, well, we did a misalignment of 0.1 to see, that's what we get, something really good within, this is 1% of error. But if you have an error of 1 degree, which is something that can happen on most of the commercial device, then you see that the error increase with the zenithal angle, and it can go quickly to more than 1% when you arrive at 60, just to give you numbers. So be careful with the alignment. Well, make your best. I mean.